Björn is head of product and also since quite a while head of the French branch of IQM. Quantum computers, a manufacturer of quantum computers. So he is dealing with the product of the future. It's already there and you can buy it, but it's not so much in use. It's the other way around. No.
Yeah, so my talk is exactly about this new technology, quantum computing, and it's a nascent technology. It's has been around on the technology and research side for quite some time, but it is now about to be introduced into the market. And the question is how platform economy can help to develop this market and to get the business going. And just as David mentioned in the previous talk, product management is about connecting technology and business. So I'm going to look on both of these elements from a slightly more strategic point of view and give this as an example of how this very new technology can develop. So here you even see one of the elements of our product, the quantum chip. But let me give you a slight overview what we're looking at. So I'm going to talk a little bit about the technology side of things. So what is the promise of quantum computing? What do you want to achieve with that? Then I'm going to look at the how platform economy can help to develop the business around quantum computing. And then I'll show how IQM, the company IQM, how we do it and how we employ that. So what is the promise of quantum computing? What are we actually talking about? We are looking at high performance computing as a problem or a marketplace. This is basically what you know is these big data centers and supercomputers, which are doing very difficult tasks, computational tasks, physics modeling tasks, for example, climate modeling, weather forecasting, or fluid dynamic calculations. But we also have problems in genomics, for example, genome sequencing or protein structure predictions. We have a lot of financial modeling, risk analysis, option pricing, problems in computational chemistry for discovering of new materials or drug discovery. And of course, the big field of data analytics and machine learning. And all of that is done in high performance computing centers and supercomputers. And the worldwide market in 2023 for this field is $50 billion. Now, there are a number of issues here. So it's very interesting to see that over the last decade, the amount of computing power that has been provided to the world has increased by a factor of 100. And the projection is that this computing power is going to be, in the next 10 years, still going to be increased by a factor of 100. So the increasing demand in computing power is not dampened or not stopped. And the interesting thing is that even today, we spend so much energy on these computing centers that HPC computing is responsible for 2% of CO2 production in the world. That's the same as the aviation industry does. And another very interesting data point is that by 2025, we will spend the same amount of energy in feeding these machine learning programs as we need to feed natural intelligence. So the whole of humankind takes the same amount of energy as that we use in HPC centers to do calculations. That's very interesting. There's another problem if we want to continue on this trajectory. There's the end of Moore's law. So current chips that we have in mass production are between 10 and 15 nanometers in size. The best chips that we have currently, really cutting edge, are 3 nanometers, but it's quite doubtful that we could go beyond 1 nanometer. So here you see that there's really a limit to this HPC high performance computing just due to technical reasons. So that's where quantum computing comes in. That's where a new computing paradigm probably helps us to solve these problems. So what I'm trying to show here is the exponential increase in classical computing time if you go to large problem sizes. So, for example, if you have a certain molecule that you want to simulate and you add one more atom into that molecule, you'll double the computing time that you need to predict that. For these kind of problems, quantum computing, due to its special properties that it will just flash in a second, you will get actually not an exponential increase in computing time, but just a linear increase. So typically, if you look at supercomputers, it is still kind of doable that you have calculational times of around 2 weeks. That's kind of this crossover point where you see that quantum computers can become interesting. So at very small problem sizes with small computing times, quantum computers actually are not an advantage. But if you become to really big problems, then you will see, or that's the prediction, that quantum computing will really help. And where does it come from? So basically, maybe one point here. So what the industry is trying to do on the technology side is basically to move forward the performance of quantum computers by pushing forward the problem sizes that can be dealt with, which is connected to the number of qubits that we have. I'll come to that in a second. Just a flash, you can talk to me in the coffee breaks to go deeper into the technology. That's not the topic here, but the basic principle is that you move from standard bits, which are electronic switches between 0 and 1, and go to qubits, quantum bits, which are made from atoms. And they have a much richer space, which is not only 0 and 1, but a lot of in-between states between 0 and 1 and different angles that you have in these states. And if you combine these different atoms together, you get combined states which have an inherent parallelism in their computational power. And this is the power, the exponential power that is used. So for 3 atoms combined together, you basically get 8 states. And for 10 atoms combined together, you get 2 to the power of 10 states that you can work with in parallel. What does that mean on the market side? We have a worldwide HPC market, as I said, of around 50 billion dollars. Interestingly, around 30% of that is served through cloud. And currently, we have a quantum computing taking roughly 1% of that market, and which is, sums up already to $500 million in 2023. And we see the projections going into the future, which is mainly based on the fact that on the one hand side, the HPC market is rising. And on the other hand side, we see that the amount of quantum computing that is taking part of this market is also projected to be increasing by a factor of 10 due to the improvement of machines that we have. Typically, this market is served by IT integrators. And there's, of course, the possibility to serve this through cloud markets with the usual suspects here. So that is the problem space, the market we're talking about. So the question is, how can this market be developed? Because, of course, we're still in early stages. And here comes platform economy. So where do we stand in this innovation life cycle? We are very much in the beginning. So the customers that we have are innovators, and we're just about talking to early adopters. But in order to get to this big market, we have to cross this famous chasm, which is on the one hand side, of course, a technology barrier, just scaling up the machines. On the other hand, it is just reaching out and developing an ecosystem, which is currently not there. And the computing paradigm behind quantum computing is quite different than the one that you see in classical computing. Of course, you need to interact with these two domains, but it is not 100% clear for the industry how to really adopt this new paradigm. So this is the challenge. Basically, what the industry is trying to do is to scale up the number of qubits, which is shown here on the x-axis. Currently, we're in the order of 100 qubits to 1,000 qubits. So some of the major players that are in this field are like IBM, Google, Honeywell. That is where the industry in total is. Also, our company, IQM, is in the same region. We see these qubits, they are quite fragile things. So we need to improve still on the stability of these qubits. And what the industry is aiming at is to get into this green region, because that's where the first really useful use cases are, where there's this intersection point between classical and quantum computing, where quantum computing becomes really better. This is going to happen in the next 3 years. That's the projection, that's the expectation of the industry. In the press, there used to be a lot of discussion about basically cracking the RSA algorithms with which internet is encrypted. That will probably take another 5 to 10 years until we get there, because it just requires a very large number of data qubits here. Now, the point is, we are still in the early stages of the life cycle. Innovation still happens. On the same hand, quantum computers are very expensive to develop and to maintain and to operate. And therefore, we need, not everybody can afford a quantum computer to experiment with it. So obviously, this is a good way to use platform economy to help develop this ecosystem and develop this market. So obviously, putting quantum computing resources into the cloud is an excellent way to reduce entry barriers. And providing a pay-per-usage access really enables to have a cheap access to this expensive quantum hardware. But there's also algorithms that have to be tested and seen how they work out. So there's also a large set of algorithms that can be traded over these platforms. And there's also, of course, a rich tool environment that you need to develop these kind of algorithms and integrate them into your classical systems. So this is where transactional platforms actually come into play. It has an other obvious advantage. This is the maximization of the usage of these quantum computers by allocating computational tasks and managing the workload, which is not so easily done if you have your single machine in your own data center. Then clearly having development environments is very important to connect the community and to standardize this community to allow them to interact, which is usually what the players like IBM and Google, for example, do. They provide these innovation platforms by providing kits, libraries, and APIs. And there's, of course, the possibility through learning platforms and exchange platforms to have a space for sharing knowledge and exchanging between the people that develop these machines and the developers and especially the users of the machines. So if we heard before, we need to bring these two domains together as closely as possible in order to have this ecosystem develop more rapidly. And finally, it's also a possibility to develop new business models. So if actually algorithm developers use the resources which are provided through the internet, they can also put their own solutions on the cloud and start developing their own transactional platforms to make these kind of algorithms available to a wider ecosystem. So this is clearly how the platform economy and the different variants will help, and is actually already helping to develop quantum computing marketplaces. So what is IQM doing here? Short flashlight onto the company. It's a startup from 2019, has been a spin out of Aalto University in Helsinki. We are looking at developing quantum hardware, but full stack, not just the chips that you saw before, but actually the integrated quantum computers that can be used to be programmed and then execute algorithms. We have around 200 million euros capital raised, but we have already sold systems and generated a total revenue of 70 million euros. Within the 4 years, the company has been growing quite a lot to 260 people, a lot of engineers and scientists, as we saw before. And we spread out across Europe and started just a hub in Singapore. So what does the product look like at the moment? So we have started with 520 and 54 qubit systems with certain fidelities. And you see that the chips, they have to be cooled down quite a bit. So they are in these cooling refrigerators that need to be kept at a very low temperature. But apart from that, the interaction with these systems is through standard laptops. And you can have development environments where you do the algorithm programming and then they are executed. What is very important for us is that we have actually integrated these machines to HPC centers. And two important ones here are Leibniz Rechenzentrum in Germany and LUMI in Finland. Now, on the tech roadmap, we are looking, of course, at a number of qubits and error rates, but we also are looking at standardizing middleware and providing full cloud access. We do have a remote access for special customers, but in order to connect to this larger ecosystem, we also need to provide full cloud access here. So how does that look on the value chain? So obviously, if you look at the different stages here, we're integrating components to quantum computing hardware. We integrate it with software into full stack systems, and then we basically have two distribution channels: on-site integration with HPC centers. Here we use partnership with IT integrators like Atos, one of the biggest in Europe and in the world. But also cloud integration is, of course, a good possibility here. And then the end cases, the use cases that I've talked about in the very beginning of the HPC use cases are then used by the different industry verticals. So currently we're having the quantum computing platform, which is then integrated to HPC centers, which are then through cloud service providers given to end customers as platforms as services. We have this remote access, and we are going to go to a full cloud solution here so that we get closer to the end users, because getting closer to the end users also increases margins. So getting to these use cases at the end is very important for us. Also to get a lot of feedback on the usage of machines and to see what the customer problems actually are and how they think about integrating quantum computing in their environments. We are also looking at actually going into a model of quantum computing as a service where there's full access and full integration to the end user domain, which then consists not only of the algorithms which are used to solve certain customer problems, but also improving on education and consulting the end customers. And this is basically the roadmap that IQM follows in order to build this quantum computing economy for their own purposes. Here are two examples of what we have already done. So there is an IQM Academy, which is online, which allows us to attract talent and to get involved with end users. And then on the development side, we have provided an open source design tool for these quantum circuits called KQ Circuit. We also integrate with the open source platforms from IBM and Google, like Circ and Qiskit, which are the development environments here. Okay, so in a summary, I would say quantum computing is a promising candidate for contributing to reduced energy and time consumption in high-performance computing, a field that really is probably overlooked. A lot of what you do on your laptops, on your mobile phones, machine learning algorithms that are implemented there are using computing power from HPC centers. Quantum computing is still at an early stage, high investment costs and ongoing innovation, and therefore having a platform economy and tools from that platform economy will help a lot to develop that ecosystem. And we basically have three different platforms that we use: transactional platforms, reducing initial CapEx investment. We have innovation platforms that provide standards and enable collaboration between different players. And in the end, we have these learning platforms, which are very good for education because it's a very different computing paradigm here. And also to attract talent. You've seen before, we have people from 40 different nations around the world because quantum computing talent is just so rare at the moment. And that is one of the big challenges at the moment to develop this industry. Thank you very much.
Yeah, thank you very much, Björn, for quickly running us through quantum computing. Questions here in the room or from the chat? Once again, it would be best if you just unmute your mic and raise the question. Here in the room? For the audience.
Thank you for the presentation. That was amazing. And I'm really looking forward for the release of this platform. So we do use in drug discovery industry a lot those cloud services for computing, and a lot, for example, for molecular modeling of properties of drug products. And it is the easiest option is pay by use right now. How would you expect to be competitive with the current system in terms of prices?
Yeah, so the question is, of course, at which point in time will quantum computing become more effective than classical computing? And we still have, let's say, 1 or 2 years to go until we reach that juicy green region that I showed, where it will become, we have this inflection point. And then I think you will use, ideally, the quantum computing resource just as classical computing resources through the cloud. You will probably not even see that your specific algorithm is executed on a quantum computer. You will just see that the execution times are lowered significantly, and that will then lead to, let's say, a clear impact on your cost side, because so far you probably spent 10 million euros for a 2 weeks employing of an HPC center, and then you can probably halve the price, and so then you generate value on the end user side, and then this is the actual business case for the end users, which will translate into the business cases for the quantum computing resources. Of course, cloud is good to experiment, especially in the case of, let's say, drug discovery or also other, let's say, financial industry. Very often we see that they build their own data centers, their own supercomputing centers, because of data security reasons. And these companies do not want to put their data and their IP onto the internet or share it over, let's say, US cloud providers. So that's one of the big things. We also see that we are still clearly aiming to do on-premise integration of our quantum computers because of these reasons that you have there.
I had a IT security conference in March, and there were 2 presentations on quantum computing, and one was about anticipating the ability of quantum computers to crack the cryptography, and they're already investing now a lot of money in building up the post-quantum cryptography. So they're taking that very serious on the other side, and possibly when your computers will be on that level,
yeah,
the defense will also be on the same level because it was developed parallel.
Yeah, that's right. So it is a recommendation from NIST, the National Institute for Standards in the US, to already start using quantum safe encryption mechanisms. Because obviously, I think the strategy is kind of clear. You collect all the data you have now, store them on a big server, wait 10 years until you can crack them, and then you have access to a lot of plans. And if you look at the, let's say, defense or aerospace industry as examples, here you have life cycles of 30, 40, 50 years. So it still is very relevant to get these plans and decipher them. So
I understood it's a kind of race. So
yeah, it's a race, yes.
Quantum safe cryptography is currently not available, so it's not existent right now.
And you can see, I mean, it's just, it is just around the corner. And if I look, my old industry, aerospace, like 10 years development cycles were not were nothing. And we're talking here about 2 to 3 years for the first quantum applications to become real. And let's say, even if it takes 10 years for these crypto problems to occur, they need a lot of also infrastructure and structural changes in the industry.
Okay, everybody's hungry. I have just came to my mind my personal last question. Do the established computer manufacturers also invest in that area?
They do. IBM is one of the biggest investors there, but we have Fujitsu, Dell, NEC, like many of them are at least.
And will they market under their own brand or?
Yes, usually they do.
So you have tough competition.
It is true, but many of these manufacturers do not build their own quantum computing labs, but they will then collaborate with startups like us and see who in the race will win, because there are, let's say, roughly half a dozen of viable technologies out on the market. Superconducting, like we are doing the same technology as IBM and Google, is one of the most promising ones, but there are others as well. And currently it's a little bit in this innovation field. You keep your options open and you don't bet on a horse, but you bet on the race. So that's what these companies are doing.